Welcome to the High Voltage AI podcast. We're on day 2 of our week-long series, really doing a deep dive into the huge impact of AI and data centers on our electrical grids. Yesterday, we started unpacking what we called the data center tsunami and why 75% of utilities are really scrambling to keep up. Today, we're zooming in on something truly staggering, this projected jump from 4% to potentially 15% of the total grid consumption being driven by these demands. Just picture this. A planner at Duke Energy, looking at the 2030 forecasts, literally had to double-check the math. The numbers just seemed impossible. We're talking a 300% increase in data center electricity demand in just 6 years. In their territory alone, this isn't just, big numbers. It's a fundamental shift in how we plan, how we power everything. And the source material we're digging into today makes it really clear. The tsunami, it's not coming. It's already here. It's reshaping the grid right now.
It really is. And understanding what unprecedented actually means, in real numbers, that's absolutely critical for everything, right? Load forecasting, system planning, those huge infrastructure investments. So today we're going to break down those exact numbers, drawing from our source, breaking down the numbers from 4% to 15% grid consumption. What's really fascinating, I think, is just the speed. How fast this landscape is changing. It demands a completely new way of thinking about the grid.
Okay, let's unpack that. This consumption explosion, let's look at the numbers. Current state, 2024, versus where we might be in 2030. So right now, U.S. data centers, they're using around 200 terawatt hours, BWH, a year. And a terawatt hour, just for context for you, that's a massive unit of energy. Think output of whole power plants, consumption of large regions. So 200 TWH, that's about 4% of total U.S. electricity use. To put that in perspective for you, that's roughly the entire state of Texas's electricity demand for a whole year.
Wow, yeah.
And get this, it's growing at 15-20% annually. The overall grid, it's growing at maybe 2-3%. It's like a sprinter next to a jogger.
Exactly. And if we connect that to the bigger picture, fast forward to 2030, U.S. data center consumption is projected to skyrocket. We're talking 600 to 800 TWH annually. So that means it jumps from 4% to potentially 11-15% of total U.S. electricity consumption, which is just, it's more than Canada's entire electricity consumption today.
Well, in all of Canada.
The whole country, yeah. Which raises that big question, what kind of new capacity does that actually require? We're talking about needing 400, 600 TWH of new capacity. That's like building 100 or more large power plants. To make it even more real, our sources suggest it's like needing to build the equivalent of one large nuclear power plant every single month.
Every month.
Every month for the next 6 years, just to serve data center growth. And that's on top of keeping up with all the other growth on the grid.
Wow, a nuclear plant a month for 6 years. That's genuinely mind-blowing. So what's fueling this just insatiable demand? What's behind these staggering numbers?
Well, the primary driver, no question, is the AI revolution. I mean, think about it. Training just one large language model like GPT-4, just the training part, that consumes about 1,300 megawatt hours.
Okay.
To put that in everyday terms for you, that's enough electricity to power 120 American homes for a whole year.
Just training one model.
Just training it, learning.
So the real energy hog is when these things are actually running, doing their job.
Precisely. The real electricity demand comes from inference. That's running the models for millions, billions of queries daily. Take ChatGPT. It processes over 100 million queries every single day. Each one of those queries, it takes the computational power equivalent to running maybe 10 Google searches.
10 searches per query. Wow.
Yeah. And when you scale that across every AI application out there, AI alone is projected to account for 50 to 70% of all new data center electricity demand through 2030. This is an unprecedented surge.
And it's not only AI, right? You mentioned other factors like the pandemic effect.
Absolutely. The pandemic accelerated cloud migration massively by maybe 3-5 years, some estimate. So big companies moved their stuff to the cloud in just 2-3 years, something that might have taken a decade before. That's a huge load shift.
Right. Compressed timeline.
And then there's edge computing. Some thought edge might reduce the need for huge central data centers, but actually it's multiplying the number of facilities needed. Every major metro area now needs multiple edge sites for things needing super low latency, right? Autonomous vehicles, augmented reality, real-time gaming.
So more facilities, not fewer.
Exactly. And we can't forget cryptocurrency, blockchain. Bitcoin mining alone uses about 150 TWH annually.
Wait, Bitcoin alone, 150 TWH?
Yeah, that's about the same as the entire country of Argentina consumes.
Argentina?
Yeah.
Just for Bitcoin. That's okay. That's a huge load too. But are these demands AI, cloud, edge, crypto, are they spread out evenly? Or are they piling up somewhere specific?
That's a really critical point. The growth is definitely not evenly distributed. It clusters. Data centers tend to group together in specific regions. Why? Well, things like great fiber connectivity are key. Also, a climate that helps with cooling, the cost of electricity, and being near major population centers. This concentration, it creates these localized grid strains, much harder to handle than if the growth was spread out. These become real hotspots.
Hotspots, okay. And these clusters, they must be hitting certain areas really hard, making the challenge unique there. Can you give us some examples?
Sure. Let's look at Northern Virginia, Loudoun County, right? They call it Data Center Alley. Current capacity there is around 1.8 gigawatts, projected to jump to over 4.5 gigawatts by 2030.
Wow, more than double.
Yeah, 150% increase in regional demand from data centers. It means they basically need a complete transmission system rebuild, not just tweaks, a total overhaul.
Okay, where else?
How about Texas, specifically Dallas-Fort Worth? They're looking at going from about 1.2 GW now to 3.2 GW. That's a huge chunk of ERCOT's projected 150 GW peak demand by 2030. It means massive generation and transmission expansion needed across the state.
And California, Silicon Valley.
Right, Silicon Valley and the Bay Area. Currently around 800 megawatts, projected to hit 2.1 gigawatts. That's a 160% increase. And that's despite California having really aggressive energy efficiency programs. The big challenge there, urban transmission constraints. It's just incredibly hard to build new power lines in dense areas like that.
Makes sense. Any others?
One more key one, the Atlanta metro area. Currently about 600 milliW, expected to reach 1.8 GW. That's a 200% increase just in the metro area data center load. It's forcing a major distribution system rebuild, not just transmission, but the local delivery network too.
So these massive concentrated loads, it sounds like they completely break the old ways utilities plan things. Traditional forecasting relies on gradual, predictable growth, right?
Yeah.
This is anything but.
Yeah, their old playbooks are pretty much obsolete in these areas, which raises that crucial question. How do utilities adapt? Think about traditional industrial growth. It's maybe 2-5% a year. It unfolds over decades, nice and slow, predictable. Data centers, you get 50, 100, even 200 megawatts of new load, enough for tens or hundreds of thousands of homes added in a single year when a facility turns on.
Bam. Instant load.
Exactly. So infrastructure has to be sized for that immediate full load. You can't ramp up gradually. Imagine planning a small neighborhood road and suddenly a 6-lane highway's worth of traffic just appears overnight.
Yeah, okay. That analogy works.
Then there's the load factor disruption. Load factor is basically how consistently something uses power compared to its maximum potential. Your typical office building might run at 40-60% load factor. It's busy during the day, quiet at night and weekends. There's variation. Data centers, they run flat out. 85-95% load factor, almost 24/7, 365, minimal variation.
Always on.
Always on. Which means for the grid, their peak demand is their sustained demand. This basically wipes out the diversity benefits utilities use to count on the fact that not everyone maxes out their power use at the exact same time.
Got it. No more averaging out.
Right. And that ties into the last point. Coincidence factor elimination. Planners traditionally relied on maybe 60-80% coincidence. Not everyone hits peak demand simultaneously. Like, not every house turns on the AC at the exact same second. Data centers, because they run continuously, they operate with 95% coincidence. They are all on all the time. So utilities now have to design for that worst case scenario, not a statistical average, which means building much more robust, higher capacity infrastructure.
Okay, that's, terrifying for planners. So what does this actually mean in terms of concrete and steel? What do we need to build?
Well, connecting this back to the grid infrastructure, it means needing an additional 200, 300 gigawatts of new transmission capacity, the price tag for that, somewhere in the range of $400-600 billion over just 6 years.
6 years. But don't transmission projects usually take way longer?
Exactly. They typically take 7-10 years, sometimes longer, with siting, permits, construction. And here's the kicker. About 60% of this new capacity is needed in just 10 metropolitan areas, the very places where it's hardest and most expensive to build.
Okay, that's transmission. What about actually generating the power?
For generation, we need maybe 150 GW of firm capacity, reliable power. To put that in perspective for you, that's like building 200, 300 new large natural gas plants. Or if you're going the renewables route, maybe 400, 600 GW of solar or wind, plus over 100 GW of battery storage to back it up. These are immense numbers.
Huge numbers. And the local distribution systems.
They need a total transformation, too. Not just reinforcing lines, but often upgrading voltage levels, maybe to 69 kV or even higher, just to serve these massive loads. We're potentially looking at 500 or more new distribution substations, enhanced protection systems, systems. And remember, critical gear like those big power transformers, they have 18, 24-month lead times. That adds huge pressure when the data center wants power now.
So this is stacking up to be a massive economic reality check. The investment needed is just very staggering.
It really is. Just for the utility infrastructure side, transmission, distribution, generation between now and 2030, we're looking at $600, $800 billion for T&D, another $600 billion for generation total. Yeah. Somewhere between 1.0 and 1.4 trillion dollars. Yeah. And that cost has to go somewhere. It translates potentially to a $0 to $10 or $2.04 per kilowatt hour rate increase for all customers, a noticeable hit on everyone's bill. And that's just the utility side. The data center customers themselves, they're likely spending another $2-3 trillion through 2030.
Wow.
For building the facilities, their own on-site electrical gear, backup generators, it's huge all around.
But maybe the toughest part isn't just the money, it's the speed, right? The timeline compression you mentioned.
Absolutely. That might be the single biggest challenge. Data centers operate on tech timelines. They need to go from choosing a site to having power in 18-24 months. They want immediate interconnection. Speed is key for their business. Utility infrastructure timelines. Totally different world. 7-10 years for transmission, 5-7 for generation, 2 to 4 for distribution upgrades. Even just getting the big transformers takes 18-24 months.
So the timelines are completely mismatched.
Completely. And this mismatch is forcing utilities into making speculative infrastructure investments. They almost have to build it, hoping the data center load comes, rather than the traditional model of waiting for confirmed demand before building. It's a fundamental shift in risk. Utilities aren't just service providers anymore. They're almost becoming proactive, speculative infrastructure developers.
That's a huge shift, making billion-dollar bets on future demand. So what does this mean for you if you're an engineer, a planner, anyone working in this space? How does this change the day-to-day job?
Yeah, that's a critical question for engineers. If you're doing load forecasting in these hotspot regions, forget the old regression models. They just don't work for this. You need to move to scenario-based planning. Model these step-change load additions. Focus heavily on analyzing the interconnection queue, who's asking for power when. Imagine being that forecaster. Your models, based on decades of slow growth, are useless when a single project adds 500 milliW and 18 WEMPs. It's a whole new game. Expect way more uncertainty, maybe 20-30%.
Okay, so forecasting is out the window. What about system planning?
For system planning, you absolutely have to design for immediate full load operation, no gradual ramp up. Plan transmission for maybe 2 or 3 times the current peak demand in these data center zones. Seriously, think about pre-building some infrastructure. And you have to bake in the data center's reliability needs, often N1 or even N2 resilience, right into your core planning assumptions.
N1, N2 meaning the system can handle losing 1 or even 2 key components without an outage.
Exactly. Much higher reliability than for typical customers. And for infrastructure investment itself, you've got to accelerate equipment orders. Think modular, scalable design so you can adapt. Evaluate using higher voltage levels from the start, even if not needed immediately, to allow for future growth. And always, always plan for those 95% plus load factors.
And the money side. Financial planning.
Utilities need new rate structures for these unique high load factor customers. They need to figure out alternative ways to recover the costs of these speculative investments, maybe new customer contribution policies for dedicated infrastructure. Bottom line, plan for massive increases in capital spending. It's a totally different financial picture.
Okay, so bringing it all together, this jump, 4% to 15% of grid consumption, it's more than just growth. It really is a fundamental transformation of how our grids work. The numbers are just...
Yeah, mind-bending.
And the ripple effects are everywhere.
Yeah, the key takeaways are pretty stark, I think. First, scale. We're adding load equivalent to building over 100 large power plants in just 6 years. Second, speed. Infrastructure timelines have to shrink dramatically, from 7-10 years down to maybe 2-3, which seems almost impossible. Third, certainty. Planning shifts from predictable, gradual growth to these sudden, massive step changes, often with significant uncertainty. And fourth, investment. We're talking well over $1 trillion in utility infrastructure alone needed by 2030.
A massive challenge.
It is. And the utilities, the engineers, the planners who recognize this seismic shift and adapt their thinking, their processes, they'll be the ones who can manage this. Those who try to stick to the old ways, apply traditional approaches to this, well, they're going to struggle to meet customer needs, struggle to maintain reliability. The question really isn't if this transformation will happen. It's happening. The question is, can our engineering, our planning, our regulations evolve fast enough to actually meet the challenge?
That is definitely something to mull over, especially seeing these projections turn into real-world engineering needs that are actively reshaping our grid right now. Okay, tomorrow, we're going to continue our high-voltage AI deep dive. We'll get even more technical. We'll explore the specific distribution system design challenges, talk about voltage level selection, and look at some technical solutions that utilities are actually putting in place to cope with this new reality. Hope you can join us then.